Swayam Prabha. Digital India. Educated India.
Namaskar. Yesterday we spoke about the various circuit elements like resistance, inductance and capacitance. We saw their properties and we also saw the governing equations for those elements. We also discussed the Ohm's law. Now today we will continue our that discussion and try to see what are other basic laws which are important for the analysis of electrical circuit. Now the Ohm's law itself is not sufficient to analyze the circuit. So the two laws, that is Kirchhoff's two laws, were developed which are sufficient and powerful set of tools for analyzing the large variety of electrical circuits. What are these two laws? These two laws are Kirchhoff's current law and Kirchhoff's voltage law. The first one, that is Kirchhoff current law, is based on law of conservation of charge. That means that the algebraic sum of charges within a particular system cannot change, and this Kirchhoff current law states that algebraic sum of currents entering in a particular node or in a closed boundary will always be 0. How you will represent it mathematically? You will represent it like summation of In, that is current flowing into nth element, is nth, basically we will say nth branch of the circuit. So In is the current flowing in the nth branch. So KCL says that the summation of all the currents flowing in the branch, in all the branches, is equal to 0, and the In, that is the subscript for current, is varying from n is equal to 1 to capital N. What is capital N? Capital N is the total number of branches connected to that particular node where we are analyzing the circuit, or you can say that it is total number of branches coming in or out from a particular closed boundary. Now this, in this law, current entering the terminals are regarded as positive and the currents which are leaving the node are considered to be negative. So if you see this particular figure and you try to apply the Kirchhoff current law at the node where the currents are coming in and going out, what you can write? The current I1 is going inside the node, so it is positive. Current I2 is coming out, so it is negative. Similarly, I3 is positive and I4 and I5 are negative, and the sum of all the currents would be equal to 0, which is satisfying the particular equation of KCL. Or alternatively, you can write that I1 plus I3 is equal to I2 plus I4 plus I5. So from this, what you can conclude, that the sum of currents entering a node is equal to sum of currents leaving the node. Now let us talk about the second law of Kirchhoff, and this second law is based on principle of conservation of energy. This Kirchhoff voltage law states that algebraic sum of all the voltages around a particular closed loop would be 0. So in this case, this Vm is the voltage across a particular element connected in a loop, and if you sum up all the voltages in a particular loop across all the elements, then you will get the summation of voltage would always be 0, and M varies from 1 to capital M, where capital M in number of voltages in the loop, and Vm that we have considered is the mth voltage. Now, how you will analyze the Kirchhoff voltage law in a particular circuit? Let us see this particular circuit where all elements are connected in a particular loop. So, this loop is closed loop. If we apply Kirchhoff voltage law for this particular loop, what we will write? Let us start from V 1, because since we are starting from V 1, that is, we are going inside the negative terminal of voltage source and coming out of the positive terminal of voltage source. It means that the voltage is rising up during negative to positive terminal. So, we represent it like minus of V 1, and then for the resistance V 2 is positive, because we are entering into the positive side and coming out of negative. So, here it is a voltage drop. So, for voltage drop we are writing as positive, and voltage rise we are writing as negative. For voltage V 3 we will again write as a positive, because the across the resistance we will see the voltage drop, and then again when we go across this voltage source, the voltage is again rising from negative to positive. So, we have taken voltage as negative of V 4, and then again across resistive element V 5 it is voltage drop. So, we will say as positive V 5. Now, if you rearrange the elements in this equation, we can say that V 1 plus V 4 is nothing but V 2 plus V 3 plus V 5. Now, from this what you can conclude, that sum of the voltage drops in a particular loop is equal to sum of voltage rises. Now, let us talk about the series resistors and the voltage division concepts. Let us see the circuit below, where two resistors are connected in series and the same current is flowing through both of the resistors, because those are connected in series and it is completing the loop. So, which law you can apply? You can apply Kirchhoff voltage law. Now, the current is same. So, voltage drop across resistor R 1 can be written as V 1 is equal to I R 1, and similarly voltage drop against resistor in resistor 2 would be I R 2. So, total voltage from Kirchhoff voltage law you can write V is nothing but V 1 plus V 2. Now, since current is common, you can take current out and you will get I R 1 plus R 2, which is nothing but I R equivalent. So, this equation, this particular segment of the this particular equation will be represented with the help of this figure, where we have a V voltage source and the equivalent resistor of both of the resistors R 1 and R 2. So, what we can write? R equivalent is nothing but R 1 plus R 2. Now, if you generalize this particular equation, you can extend it for multiple resistors. So, equivalent resistance for any number of resistors connected in series would be the summation of individual resistances. So, suppose if you have n resistances connected in series like R 1, R 2 up to R n are there, what would be the equivalent resistance? Equivalent resistance would be summation of all the resistances connected in the series. So, in short form what you can write? You can write summation of I is equal to 1 to n R I. I varies from 1 to n, which tells how many resistors are connected in series. Now, the voltage is divided among the resistors is directly proportional to their resistances. How you will say? Suppose there is a resistor R n and voltage across that resistor is V n. So, what you will write for voltage across R n V n is nothing but R n divided by sum of all the resistances in the loop multiplied by V. So, here you can say that the voltage division is happening because of the resistances connected in series. Now, let us talk about the case where the resistors are connected in parallel. There we will say that the current division will be followed. So, let us take now this figure where voltage is connected to R1 and R2 both which are in parallel. So, current flowing through R1 would be I1 and current flowing through R2 would be I2. So, since these two are in parallel, what you can apply? You can apply Kirchhoff current law. So, basically one important thing which you can always take it as a thumb rule is that whenever you see elements connected in series, you can simply apply Kirchhoff voltage law, and when you see the elements connected in parallel fashion, you can use Kirchhoff current law. So, these are the two important laws. Based on the circuit you can apply them. So, now let us see this particular circuit where current is being divided into I1 and I2. I1 is flowing through R1 and I2 is flowing through R2. Since voltage is same across R1 and R2 both, you can simply find out the value of I1 is nothing but V by R1 using Ohm's law. Now, similarly for I2 also you can write I2 is nothing but V by R2. So, finally, V would be 1 upon R1 plus 1 upon R2, or simply you can say V by R equivalent. This you can represent using the equivalent figure where voltage is connected in series with resistance R equivalent. So, what you can write now? 1 upon R equivalent is nothing but 1 upon R1 plus 1 upon R2. Now, if you want to generalize it, what you can write? Suppose if there are n resistances in parallel, then 1 upon R equivalent is nothing but 1 by R1 plus 1 by R2 and so on up to 1 by Rn, or in mathematical terms you can write like summation of I is equal to 1 to n of 1 by Ri. I is ranging between 1 to n, where n is number of elements, that is number of resistors connected in parallel fashion. So, how you can summarize this particular aspect? This says that equivalent resistance of any number of resistors connected in parallel is the reciprocal of individual resistances. So, reciprocal of individual resistances is 1 upon Ri, and then you will sum up, and whatever you will get finally you will take again the reciprocal of same, and you will get the value of equivalent resistance, right. It means that you can simply write R equivalent is nothing but reciprocal of the summation of the reciprocal of individual resistances, right. Now, when you talk about the current division, the circuit which you saw in the previous slide, that is in this figure, if you apply current division, you will get the currents flowing through the individual resistors, which are expressed like I1 is equal to IR2 upon R1 plus R2 and I2 is equal to I R1 upon R1 plus R2. Now, you will ask how I will determine these values. So, let us see how you can find out the value of I1 and I2 by seeing this particular figure. So, now you know that I is nothing but I1 plus I2 and voltage V is anyway applied across both of the resistors. So, V is nothing but I1 R1 or I2 R2, right. It means that I1 R1 equal to I2 R2. So, from here you can find out the value of I2, that is nothing but I1 R1 by R2. Now, this value of I2 you can put here. What you will get? I is equal to I1 plus I1 R1 divided by R2. Now, if you simplify, what you will get? R2 plus R1 by R2 into I1. So, finally, what is the value of I1? I1 would be I R2 divided by R1 plus R2, and this is what you got here. Similarly, for I2 also you can stabilize the relationship, which is I R1 upon R1 plus R2. So, instead of putting the value of I2, if you put the value of I1 in this equation and simplify, you will get the value of I2, that is I R1 upon R1 plus R2. Now, let us take the example. If you are asked to find the value of I2 and V2 in the circuit and also power dissipated in the 3 ohm resistor, what you will do? Since these two are connected in parallel, you can use the Kirchhoff current law at this node and try to find out what is the equivalent resistance. So, you will get equivalent resistance is nothing but 6 into 3 divided by 6 plus 3. So, total resistance of this particular loop would be 4 plus the equivalent resistance of this particular segment of the circuit. So, total R equivalent of the circuit would be 6 ohm, and accordingly you can find out the value of current I, that is nothing but voltage V divided by R equivalent, and you get 2 ampere as a current. Now, the voltage across parallel resistor is the combination of the across the 2 ohm combination, that is basically the equivalent resistance of this particular segment. So, what would be the voltage? Voltage would be I 2 pi. Since this voltage V2 is common for both resistors, so you can find out the value V2 for this combination, and then finally using the current division you can find out the value of I2. So, you get the value as 2 volt for the equivalent combination of 6 ohm and 3 ohm parallel resistors. You get the value of V2 as 4 pi, then using current division rule you can find out the value of current I2, and now using the formula P is equal to V2 I2 you can find out the value of power dissipated in the resistor. Now, let us talk about the series capacitors. Now, consider the circuit below where there are n capacitors connected in series. So, you can see that you can use Kirchhoff voltage law because these are connected in series. So, when you apply Kirchhoff voltage law, you get V is nothing but V1 plus V2 and so on up to Vn, because these voltages are the voltage across the individual capacitors. Now, what is voltage V? Voltage V for the kth capacitor can be defined as 1 upon Ck integral time t naught. T naught is considered to be the initial time, and up to t the time at which we are analyzing the circuit multiplied by I times I dt. So, this is something which we discussed in the previous class, where we analyze the various resistor, inductor and capacitor elements. So, using that particular formula, we can say that V k is integral of 1 upon C k T naught to T I dt plus the initial voltage which is there across the capacitor. Now, this is for kth capacitor. If you add up the voltages for all the capacitors which are connected in series, you will get the value of total voltage V, and that is nothing but 1 upon C 1 T naught to T integral I dt, because current I is same in all the capacitors, because it is in loop. So, when you rearrange this particular equation, you will get 1 upon C 1 plus 1 upon C 2, you can club all of the capacitances in outside the integral, because these are the constant quantities, and then T naught to T I dt V 1 T naught, because this is the common, and then the initial voltages. So, what you can write? You can write 1 upon C equivalent T naught to T I dt plus V T naught. Now, if you compare these two, you will easily conclude that 1 upon C equivalent is nothing but the summation of the reciprocal of individual capacitances. So, you can simply write the 1 upon C equivalent is nothing but summation of 1 upon C I, and I varies from 1 to n, that is number of capacitors connected in series. So, now what you can say, equivalent capacitance of n series connected capacitors is reciprocal of the sum of the reciprocal of individual capacitances, that is C equivalent is nothing but reciprocal of the sum of the reciprocal of individual capacitances, right. Now, if you compare with the previous discussion related to resistors, you can observe that capacitors in series combine in the same manner as you see resistors in the parallel. Now, let us talk about the capacitors which are connected in parallel. So, here what you can do? You can simply apply Kirchhoff current law, and you can find out the value of equivalent capacitance. So, when you apply Kirchhoff current law, you know that the current flowing in the ith capacitor can be written as I k is equal to C k dV by dt. This is what we saw in the previous lecture. So, if you sum up all the currents, it will be equal to current shown in the circuit. So, that is the total current is nothing but I 1 plus I 2 to I n. So, when you sum up, you will come to know that the C 1 dV by dt plus C 2 dV by dt and so on is the total current flowing in that particular circuit. If you sum up, then you can write like C equivalent dV by dt, and eventually you will say that C equivalent is nothing but summation of individual capacitances which are connected in the circuit in parallel. So, what you can say, equivalent capacitance of n parallel connected capacitor is nothing but the sum of the individual capacitances. So, now if you observe the correlation of the circuits related to resistors and the capacitors, you can say that resistors connected in parallel are combined in the same manner as the resistors in series. Now, let us talk about the inductors. Suppose the inductors, there are n inductors which are connected in series. So, what you can apply? You can apply Kirchhoff voltage law, because these are connected in loop. So, what you can write? V is nothing but the summation of individual voltages across the individual inductors. So, as we know that Vk is nothing but Lk di by dt, I is same in all the inductors. So, what you can write, V is nothing but L1 di by dt plus L2 di by dt and so on. So, when you sum up the all the inductors, you can simply write I is I from 1 to n summation Li di by dt, and that can be write as L equivalent. From this what you can conclude that L equivalent is nothing but summation of all the individual inductances connected in series in that particular circuit. So, equivalent inductance of n series connected inductors is sum of the individual inductances. So, if you correlate with the series combined resistors, you will say that the inductors in series combined will have equivalent inductance in the same manner as the resistors which are connected in series. Now, let us talk about the inductors connected in parallel. So, in this figure you will see that these inductors are connected in parallel. So, when these inductors are connected in parallel means you can apply Kirchhoff current law. So, if you apply Kirchhoff current law, you will get I, that is the current coming from the voltage source, is nothing but the summation of individual currents flowing in the individual inductors. And finally, the objective is to find out the value of equivalent inductance of the circuit. So, what you have to do? You have to find out the value of current flowing individually in each inductor. So, you can simply write I k is nothing but 1 upon L k T naught to T V dt. Now, since you know that V is equal to L di by dt, so I can be written in integral form, right, and the same has been utilized here to find out the value of total current. So, what you have to do? You have to just sum up the individual currents flowing in the in each inductor. So, voltage is same across each inductor. For first inductor we will write I 1 is nothing but 1 upon L 1 T naught to T V dt plus I 1 T naught. This is something which we say that the initially we are assuming that at time T naught there is some current in the inductor. So, that is considered to be as a initial condition for that inductor 1. Similarly, for inductor 2 also we will write 1 upon L 2 T naught to T V dt plus the initial current flowing in the inductor, and when we will sum up all the elements we can simply write 1 upon L 1 plus 1 upon L 2 plus L n, because these are the constant quantities we can take it out. Then T naught to T V dt integral plus sum of all the currents which we see flowing in the individual inductor at time t is equal to 0. So, what we can write? We can write 1 upon L equivalent T naught to T V dt plus I T naught. Now, if you compare these two, you can simply write 1 upon L equivalent is equal to 1 upon L 1 plus 1 upon L 2 up to 1 upon L 1. That is nothing but you can simply write the summation of 1 upon L I from I is equal to 1 to n. So, what you can say? Equivalent inductance of n parallel connected inductors is reciprocal of the sum of the reciprocal of individual inductances. That means that L equivalent can be simply written as reciprocal of the sum of the reciprocal of individual inductances, right. So, what we can observe? We can observe that inductors which are connected in parallel are combined in the same manner as the resistors in parallel. So, we saw the parallel and series combination of all the three resistors, capacitors and inductors. So, in next class we will try to find out the phasor relationship between these elements, that is the voltage and current phasor relationship for resistor, capacitor and inductor, and then we will stabilize the relationship of impedance for the sinusoidal varying voltage and current. So, we close this session today, and next class we will carry forward with the phasor representation of these quantities. Thank you.